The idea is to just use few slides to illustrate the context of what I'm going to present today. That is really at the early stages, but I think it's quite a demonstration of how you can use this in maybe an unconventional way. So first of all, the context is pretty much scientific. I'm a physicist actually, and working as a technologist at INFN, that is the National Institute of for Nuclear Physics in Italy. And we have, so our clients, if you want, are scientists. And in the context of the National Center for Supercomputing, we have distributed resources all over the places in Italy. And not only physicists are our clients, but any different kind of science domain that you see here. So all of this to quickly introduce the context. So we are working hard in the part of the cloud computing for science. But you saw from the title that I'm talking about FPGA. So why is that? So first of all, our expertise at the University of Perugia, but at INFN in general, also led this kind of communication and cross-fertilization between a field that is really bound to the hardware, but also can be leveraged by science. So in this particular case, the work presented is in the domain of the Bond Machine project, that Bond as an ecosystem for generating and synthesizing architectures for FPGA. So building a composed architecture, so hybrid processor on top of FPGA and normal processor. So that's the context in a nutshell. And again, now you should have yet another question, why we are evaluating Dagger for this kind of workflows. Well, everything starts from a very particular case study that we have for FPGA, that is the machine learning inference on top of them. And yeah, it comes with some pretty useful features that are starting from the faster processing speeds and the lower consumption with respect to GPU. But again, they are difficult to program. So there are different kind of frameworks that have been made available in order to start from a model that you train on normal circumstances, so on your battery of GPUs, and you create your model, and then these frameworks called HLS framework translate this kind of architecture into something that is actually programmable on top of an FPGA board. So that would be awesome, but again, we found some problem that we would like to solve and to address. The first one is that the part of the building of the firmware for the FPGA and all the ecosystem around that is very vendor specific at the moment. And also there is no easy way to share for any kind of user or different communities the common knowledge on that kind of framework and port that into other FPGA boards, for example, or also to extend this for other science domains. So the idea was actually, well, this kind of workflow and issues rang some bells, and we really think at the moment that we need something similar from the DAG perspective, so from the workflow perspective to what we do usually in the cloud environments with the containers. And let me explain a bit better what I mean. So we want in other terms to start from our experience on the cloud and other experience, other part of the experience on FPGA, to try to construct this kind of chain that you find here in the box. So on the green box, you have the description of your architecture or your actually your components that you want to build somehow. And the build instruction can be different for different boards. So you can provide the very same green box with different black box. And then with this couple of information, you can go to the blue engine if you want. And with this set of instruction tells, okay, now let's build the firmware, and more importantly, put it in some place that I can recover and share with others. That for us, it would be a winning choice if this place is any container registry that we already have for containers. So that's the key point for the blue box. And then once we achieve the blue box, that is the demo that I'm going to show in a few minutes, then we are ready to go on the yellow box and say, okay, I want this particular firmware for this particular board. I want to download it from the container registry. And then after that, you can load on my board locally. But more importantly, all of these yellow points now can be also delegated to a cloud environment where my precious FPGA are stored, and everything can be automated because now you have the full chain well coded and well established, and you can also delegate whichever part you want in different places. So all in all, what's the plan for us? So it's kind of creating a command line where we use a logic that is already well established in the cloud world and trying to replicate this in a FPGA hardware world. And starting from the main problem, we have different board with different firmware for the same algorithm. So the idea was, okay, how we can hack somehow a container image in order to put in the architecture part all the information we need for the FPGA board, vendor, and model. So instead of having multi-architecture container images, we have multi-architecture firmware artifacts. So that was the desiderata. And in this, we will see in just in a few seconds that Dagger helps a lot with all the building machine that actually, I'm joking in the title, we hijacked to do something that trick the container registry to think that the image is really a container image for a certain architecture, but instead that architecture, it doesn't exist, but it can be selected from a dedicated custom command line interface that we provide in what we call the BM build kit. So, all in all, the components are in this way in our initial design. And again, let me stress that is at a very, very early stage. So we have draft for all these pieces. And the first draft of the BM build kit on the right is what we implemented in Dagger. We can also think to extend this model also to the command line, for example, including other modules. But here we have some showstopper that maybe if we have some time, I can take the occasion to highlight at the end of the presentation. So it's nothing complicated. You can recognize many similarities with the container registries in general, but the core of the demo is this one. You receive instruction on how to build stuff, starting from some code and from a model for a board, and then here you build. First, you build the firmware, and then you build the artifacts if you want. That is an image, a scratch image with the firmware, with the code related, and with some architecture related to the request for the board. So if this wasn't confusing enough, now it's time for the demo. Let's see how it can go. I have here a board, pretty small and cheap board that I have just erased before starting, so it is not blinking, and just let's see how it goes. Okay, so before going ahead, let me show where the module is published. So we published this module with, you can see already some typo here in the description, but again, if you can find if you type VM build kit, and at the moment it has two main methods. The first one is the build one, so the one necessary for selecting the spec for the device and saying, okay, my final container image, my final artifact will be called in this way. And the context, so the content of what you should build with this spec is inside this folder, local folder on the host. Now notice that the cool thing of all of this method, also even if it's a draft, is that we have a logic for the build that we can separate and so containerize with different models in place. Now we have a lattice one and another and the Alveo model one, but you can increase and put whatever image with a makefile that can build your firmware. And then we have a push stage. And the push stage is the smart one. So it's taking the target image that you indicated, check if the index of that image contain the architecture you want. And if not, it will append a new architecture. So the idea is that I share my code with my colleague that has a different model of board, and it will produce another, maybe another kind of firmware for the its board, and we can put everything together on one single image with all the different firmware built for different boards. So that what we envision to be pretty useful in our case. And yeah, so these are build and push, and we can see how it works in the demo directly. So I'm adding to the, adding to the terminal, I import the Dagger module, and then I say, okay, build and push in one go the device for the build for the board that is this little one, so the lattice IS40, and pushing, we can change the name, for instance, of demo v1, and then we go to the context directory. Just a second to show you that in the Dagger, in the example directory, you have really quick and dirty blinking LED firmware. And all right, so finger crossed, and we start building our firmware. And so, yeah, hopefully, yeah, you can also decide with the export command to store the firmware locally or to rely only to have it remotely. And hopefully now, if we go to Docker Hub in this case, we should be able to see, yes, that we store a version 1 of this image with this one. The first architecture you see is the artifact containing the old context directory that can be usable in certain sense. And then you have here an artifact for lattice for my board. So the first step is done, and it went well, incredibly. So I'm already happy with that. And then there is the second step. The second step is, okay, now let's suppose in reality the machine that is building the firmware for a machine learning inference, for example, is a really big machine that takes a lot to synthesize the firmware. And then in principle, you can go to another machine that in this case is my laptop, and download the result of the synthesis project phase, and install, load the firmware into the board. That is the less demanding part of all the stuff in terms of time and resources. So let's install for this. This is not yet Dockerized. And one thing that it can be limiting is that we need to access to the local device of the host. So you tell me later if there is something that will be ever possible in the future for Dagger. But let's stick with what we have already. So we have a command line capable of downloading an image from Docker app and loading the content that is a firmware object into this board. So now let me change this command. So you see load the name of our image that was Demo Dagger V1 and the architecture that I want to load in my board. So here are the most critical part of the demo. Let's see how it goes. Yeah, so it downloaded the firmware here in this folder, and I don't know if you can see that, but now this board is blinking. So I loaded the firmware into the board, and everything went well. So from one machine I built, and from the other one I downloaded and unloaded my my firmware. And I can do this wherever I want, also if this board was on the cloud, for instance. Yeah, I think that was pretty much all. One thing that we want to introduce next is kind of a BM file format, so we can describe step by step what we want to synthesize. But that's will be the next steps.